All right, everyone, let's get started. Hope you guys had a good long weekend. So before we left, we were talking about the multivariable linear model. It's an extension of what we did in the first unit, in that now we have, instead of a single feature x, we have a vector of features. In particular, there's d of them. We still have a single scalar target. Later on, we will talk about what you can do if you have several targets you want to predict at the same time, but right now we just have a single scalar target, just like in the last unit. So we're trying to predict this single scalar y using all these different variables x1 through xd, and we propose to do this using a linear model, and that means that we're going to multiply each of our features by one of these slope coefficients, one of these like beta 1 through beta j, or beta d, and then we have an intercept coefficient, beta 0. And this approximately equal to sign emphasizes the fact that the data does not perfectly fit this linear model. But when we need to come up with a name for our prediction, we're going to call it y hat. So the question for this unit is, how do we choose those prediction coefficients? And so to start down that road, the first thing we did is we came up with some matrix vector notation for this problem that will help us. And so what we did, one thing we did, I guess, to start is we first looked at how you rewrite our linear model for the data samples we have. So we have a set of data samples, which are these pairs, these XY pairs. And so if we rewrite this linear model for the data, we essentially need to put subscript I on all the x and y quantities. So that's where we get this. So now we have y hat I, which is the prediction of yi by our linear model based on the data sample, the vector xi. Okay, so now we want to write everything together in this form. So what we're going to do is we're going to take all of our different target variables, y1, or all our different predictions, y1 hat through yn hat, and stick them into this column vector y hat. And we can take all of our feature variables. So these are the features for the first sample, these are the features for the nth sample, and so on. We can stick them all into this matrix A. We also have this column of ones, and that column of ones facilitates the multiplication with the intercept, because that intercept does not multiply any features, right? It just stands alone. So finally, after defining this A matrix and this beta vector, we get this concise expression for our multivariable linear model. Prediction vector y hat is this A matrix times the beta vector. Okay, and then the other thing we said is, once our model is trained and we have our beta vector, if somebody gives us a new feature vector x, something we have never seen during training, and you want to make a prediction for that, you can do that by making this row vector where you append the 1 onto your x transpose. So you're appending this thing. And then this has the right dimension to multiply against the beta vector that you have determined from the fitting that we're going to explain next. Okay, we can call that y hat, and this is a prediction of the unknown y that we don't know what it is. It's not our training data. It's something out in nature that we're trying to predict. Okay, any questions so far on any of the setup here? All right, and then the last thing that we did last lecture was we said that our criteria for doing our fit, same as last time, is going to be the residual sum of squares. So we want to minimize the sum over our training data of the squared differences between the true targets yi and our corresponding predictions y hat I. And we can visualize this here. This is just a visualization for the case where you have two features, x1 and x2. And here's our target along the vertical axis. And all these black dots, these are the yi's. The places where those sticks cross that plane, these would be like our y hat I. Those are the predictions of yi. And then the the locations down here, this would be the xi vector, would be a 2 by 1 vector. So this is sort of describing everything here. And our objective is to adjust the coefficients beta 0, which is the intercept on the y-axis, beta 1, which is the slope in this direction, and beta 2, which is the slope in this other direction. We want to adjust those three coefficients, which will move around this plane. We want to move around that plane until the sum across all these sticks here of the squared lengths of the sticks is minimized. That's what we are doing when we minimize RSS. Okay, is everybody good with this? All right. So in general, we're going to have more than two coefficients, but geometrically, it's going to be very similar. All the intuition follows. It's just that it's hard to draw an actual figure in more than 3 dimensions. Okay, good. So let's do a little bit more in terms of linear algebra that's going to help us solve this problem and set us up for the future. So, so one of the ways that we can connect this criteria to other things that you see in other fields and so on is to bring in this concept of a norm, the norm of a vector. So the norm of a real valued vector is just basically its length. So for example, if we have, this is going to be the case where d is 3. So we have 3 dimensions of x here. We have like x1, x2, and x3. Then this would be a visualization of the vector which has coordinates x1, x2, x3. This is like x with the underline. And if I want to measure the length, the distance between that and the origin, there's different ways to measure that length, but the most common way is the Euclidean definition of length, Euclidean norm. Does anybody remember what that is mathematically?
Square root of the x2 minus x1.
Square root of the sum of the squares. Yes, exactly. So we have, in this case, we're going to have d coefficients. Well, let's not even name. X could have any number of coefficients. I'll just write general summation index j. So we have sum over j, xj squared, square root. Okay, so again, the norm measures the distance from the origin or the length of the vector. There's different ways to define the norm, but here we're talking about the Euclidean norm or the L2 norm. We will talk about some other norms later in the course, but for now, this is what we want to use. So now that we have this concept of the norm, how can I write the RSS as a norm? Any ideas? So how do I write this in terms of the norm?
The norm of the residual square.
Yes. So in this case, we can write the residual as the y vector minus the y hat vector squared. Does everybody agree? What if I want to write this in terms of beta? How can I write it in terms of beta?
Expand the y hat.
Yeah, how do I expand y hat?
A beta.
A times beta. Okay, so here we have an expression that explicitly involves beta, the unknowns, and the things we know from our training data, which are y and a. So this is setting us up to solve the problem. Okay, so all right, any questions on this formulation? Okay, so how are we gonna, okay, so let's pause to reflect what we've done. So here again, this is a very similar slide to what we saw in the last unit. The point is that we are appealing to a general recipe that you use to solve machine learning problems. The first step would be assume a model with some parameters. In this particular case, we assumed a linear model. The parameters were these different betas. We get training data somehow out in the world. Once we have that data, we can define a loss function. In this particular case, we've chosen the loss, which is the RSS, which is the sum of the squared prediction errors. And then finally, the last step is to find the betas that minimize this loss on the training data. So that's the part where we're at currently. Okay, so we're going to use the same approach that we used in the last unit, which is to exploit the fact that when we have a quadratic function like this, there's something that's special that happens at the minima of the function, which is that the slope in every direction goes to 0. And we have names for this. Last time we talked about the gradient vector. This is the derivative of this multi-input function, where if like the jth element of this vector is going to be the partial derivative of RSS with respect to beta j. So that's like a vector of slopes. When you look in one direction, that's one element of the slope. When you look in another direction, that's another element of the slope, or another element of the gradient vector. And what we said last time is that when we're at the origin, what happens to the gradient? Goes to 0, right? So that's what we're going to exploit. Now, if you think about it, the problem is actually maybe a little bit more complicated because, for example, what if I had a situation where I have a surface, a little hard to draw this surface, but a surface which is like a dome-shaped surface, right? So what happens there at the peak to the gradient? The gradient goes to 0, right? So this whole idea of let's find where the gradient goes to 0 does not always give us the minimum. Sometimes it could give us the maximum. So we might want to be a little bit more careful as to say, well, when does it give us the minimum and when does it give us something else? So it turns out, and I'm not going to get into a lot of details here, but it turns out that when you have a quadratic, which is what we have, so let's first verify that we have a quadratic. So this is the thing we want to minimize. This is our squared norm. So one important thing about the norm, let me see, maybe I could even, I'll write it on this page. So this is an important thing about the Euclidean norm. So if I have the Euclidean norm of x squared, then do you see how I can write it as x transpose x? Because when you think about what's happening here, x transpose inner product x, you get the first element times itself, which is squaring, right, plus the second element times itself, plus the third times itself, and so on. So that gives you exactly the norm squared. Right? So using that fact, what we can do over here is we can rewrite our squared norm as the argument transpose itself. And now we have a quadratic. We can expand this into the first transpose the first, which is this term. And then we get cross terms. It turns out both cross terms have this form. Maybe if I want to be really explicit, we could see that there's going to be a minus a beta transpose y, and then we're going to have a minus y transpose a beta, right? So these things, at first glance, they may look similar, they may look different. Let me just complete everything. So this is okay. So all right. So this is just expanding this into this. Okay, now when you look at these terms, although they may look different, they're actually the same. Does anybody see why that is?
Because their dimensions is about 1 by 1, so we can have them.
Exactly. So they're 1 by 1. And the second part is, what can I do to a 1 by 1? What can I do to this to get this? What do I have to do? Transpose, right? If I have a scalar, a 1 by 1, when you transpose a matrix, you basically flip it over. Rows become columns. But if I have a 1 by 1 matrix, flipping it over does nothing. So transposing a scalar does nothing. So I can transpose this, and it's identical. And once I transpose it, then remember that when you transpose a product of matrices, you have to reverse their order and transpose them individually. So when I transpose this, that's what gives me this y transpose times, oh, and I actually have a typo here. it should be, okay, so this is actually the quantity AB transpose. So when we transpose, hold on, yeah, right. So when I transpose this, I get beta transpose. Well, I guess there's different ways to do it. Let me do it. Let me do it step by step. Okay, so we could do this. This would be like beta transpose A transpose Y. And now, when you transpose this entire thing, you get Y transpose A beta. Right, so finally, we can see that this and this are the same, and we can write them together as minus 2 times this. Okay, so back to the main point is that you can see just based on inspection that this is a quadratic. You have a term that doesn't depend on betas, you have a term that's linear in beta, and you have a term that's quadratic in beta. So this is going to be some sort of what we call a paraboloid, which is some sort of parabolic type surface. But there's a question, maybe we have a question about whether this surface is like a dome or whether it's like a cup, whether it's concave or convex, right? Anybody know how you can tell? Yeah, you have to look at the second derivative, right? So if we were dealing with a scalar function, you would look at the curvature, which is the second derivative, and you would ask, is it curving up or is it curving down? But when you deal with these multi-valued functions, you have to look at the matrix extension of curvature, which is the Hessian. And the Hessian matrix is this guy. It's this matrix of double partial derivatives. And it turns out that you want this to be non-negative in a matrix sense, and that is known as positive semi-definite. We don't need to get into all these details, so if this sounds complicated, don't worry about it. We'll get back to this a little bit later in the course. But it turns out that, yes, it's easy to prove that this matrix by its form of A transpose A is guaranteed to be positive semi-definite. So we always know that for this RSS, we always have a function that curves up, or it could be flat in some dimensions, but it will never curve down. So it's enough to find the location of the gradient equal to 0 that is going to give us what we want. Okay, so that's our approach. Let me just highlight it here. Any beta that zeros a gradient is a minimum in this case. That's our approach. And so we're going to try to find, we're going to take the partial derivative of RSS, set it to 0 for every variable, and then find what those variables are. That's essentially what we did in the last unit. It's just that we have a few more variables now. Okay, any questions on anything here before we move on? Okay, great. So this is sort of a summary. We've seen all this before. So this is our RSS equation. Here I'm writing in terms of the y's and the y hats. Here is how we got those y hats. This is equivalent to, this is just the summation form of y equals a beta. So in particular, I'm looking at the ith entry of y, and I'm writing this as a sum. We saw a lot of that stuff in homework 0, quiz 0, right? So you can see why it matters. And I'm just using the ith row, jth column of matrix A. I'm writing that as little a ij. Okay, so this is what we want to do. We want to make sure that these partial derivatives equal 0 for all j, all our different terms. So the first thing to do is apply the partial derivative with respect to beta j of this. So we did this last unit. Essentially, we need to use the chain rule and the fact that differentiation is linear. So when I differentiate this, the first thing I can do is I can move my partial derivative through the sum and apply the partial derivative to this. Then I need to use chain rule. I'm going to get 2 times this times the partial derivative of this with respect to beta j. Okay, it's this guy that has the beta j dependence, and that's this. Okay, now, next thing, maybe just, this is something that often happens that trips up students, so let me try to explain this kind of carefully. The way we're writing this, we are using the variable j on the left side here to denote which variable we are taking the derivative with respect to. So j is a fixed quantity. What's kind of confusing is that up here, we are using j for a different purpose, which is using it as a temporary index to implement this sum. We don't want to confuse this j and this j, because they're actually different things. So maybe one thing we could do to make this a bit clearer is let's just redefine this j. Let's call it something else. I'll call it j prime, because that's easy to do by putting a little prime here. And so hopefully now you see there's no more j here. These are j primes. The j is over here. Okay, so the very last thing, what I'm finally getting to is I want to take the partial derivative of this guy with respect to j. So what is that? Okay, so how do I do that? Any idea what that's going to be?
A constant?
It is going to be a constant. What is it? Does anybody know what it is? Aij, exactly. So here's one way to think about it, is that there's a lot of different terms in this sum, right? There's d plus 1 different terms. Here I'm looking at a specific index j. Only one of those terms involves beta j. All the other terms involve beta j prime for some other j prime that's not j. So I can ignore all the other terms and focus only on that single term, which is the one I'm interested in. So maybe to go a little bit more step by step, I can write this. This is going to be d beta j of aij beta j. This is what I got after I threw away all the other terms in the sum. And now you can see this is a very easy derivative to take. This is just aij. Okay, and this is where we got this. This was that last step in the chain rule. Okay, so this is something that often happens. Just we'll use we'll use an index variable here, and then use it again here for a derivative. But you just have to remember that these are not actually the same thing. That in the sums you can always change the index variable because it's arbitrary, and doing that can prevent some confusion. Okay, is everybody okay with this expression? Okay, any questions? Okay. Now, it's going to help to rewrite this expression in terms of vectors and matrices. So again, this is something that you hopefully got a bunch of practice on with homework 0, quiz 0. So here, you saw exactly problems of this form. So one way to think about it is we want to maybe manipulate those quantities so that this I is like the inner index. So for example, maybe I could do like aij times yi minus y hat I, right? All I'm doing is I'm just reordering that scalar multiplication. I can definitely do that. But then you can see I is still not the inner index. Well, actually, maybe there's different ways to do this. Maybe let me back up. I think the easiest way is to notice that right here, I is the inner index. So how can I write this? I can think about these yi's as a row vector, and so I is going to be going down the columns of that row vector, and then I can think of aij here. So I is going to be coming down this way, j is going to be going across this way. So essentially, this is our matrix A. Over here, we have the difference y minus y bar transpose. Is everybody, sorry about my bad writing. Does everybody see what we're doing? I'm noticing that this inner product down these i's, that's like these inner products here. So this is, I guess the most direct way perhaps to see it is to say this is y minus y hat, that vector transpose A. That's going to be a row vector. And now, because we often work with column vectors, I'm just flipping that around into a column. In either case, I'm going to extract the jth index. So it doesn't really matter whether it's a row or a column. Okay, is it clear how we got from sum to vectors and matrices? Okay, and then we're almost done. The reason we did this is because essentially, oh, and one last step. If we want to write this explicitly in terms of betas, we can just replace y hat with a beta. So now we have this gradient expression written concisely with matrices and vectors. And in particular, this was the partial derivative with respect to the jth beta, and we know that that's the jth entry of this vector. So I want that this is equal to 0 for all j, which tells me what about this vector? That should be equal to the 0 vector, right? Every entry should be 0. So that's what we have down here. The 0 vector, this is the boldface 0, equals A transpose y minus A beta. Okay. So I'm just, this is equal to 0 for all j, gives me that equation. And now we're in the home stretch. As you can see, and I should write, this thing that's happening, this is kind of happening especially at the least square solution. So I'll put a little ls on that beta. So when I plug in the least square solution, that is what gives me this 0 derivative. And now I can just rearrange this. This is going to be A transpose y here. And then this other term is going to be A transpose A beta least squares. Because of the minus sign, I can move it to the other side. And there's only one last step to see what beta ls is. Does anybody see? Least squares equals, yes. This is whenever we get in linear algebra, this is basically what we call solving a linear system. This is a matrix. This is our vector of unknowns. This is a known vector. So we can just multiply both sides on the left by the inverse of this matrix, assuming it exists. And that will kill this, leaving beta ls. And on the right, we will have A transpose A inverse times A transpose y. Okay, so finally, we have a concrete expression for our optimal, least squares optimal beta coefficients. It's being written in terms of this A matrix, which we know how to construct from our training samples here. And then we have the y vector, which we also construct from our training samples. Okay, so any questions about anything here, solving the least squares problem or anything on this slide? Is everybody okay with all this? Okay, so just a comment. We did assume that this matrix is invertible, and there are cases in practice where it's not invertible, and then we can't use this approach directly. One of the biggest reasons it's not going to be invertible is when you don't have enough data samples. Remember, n is the number of samples, d is the number of features. So that is not typical in machine learning. Typically in machine learning, you have way more data than you have features, but there are specific cases of machine learning where it's very much this way. Like maybe you're trying to predict or estimate what's happening at every voxel in a brain, and you're using this based on some patient data you collected, and maybe you were only able to put 200 patients into some sort of medical imaging thing. You have basically 200 n, and number of voxels in the brain is maybe 40,000 or so for a lot of systems. So that's way less than this. So, and you'll actually have this in a lab that's coming up. In that case, yes, you can't do this. So we're going to talk about strategies to deal with that in unit 4, I think is the main one. But for now, we're going to assume that this is invertible, and this is how we're going to solve the problem. Yeah.
Where did you use the Hessian to confirm that it's not a maximum?
So I didn't get into the details, but it turns out that by construction, this is guaranteed to have a positive semi-definite Hessian.
Okay.
Yeah. It's just, I'm not going to get into it right now, but it's relatively easy to prove.
Okay.
You can prove that that's always going to be the case. Whenever you have like A transpose A for any matrix A, it can never have this, your Hessian can never have negative eigencomponents, eigenvalues. Okay. Great, so that's basically, in some sense, that's solving the problem where we set out to solve. The next question we could ask, same question we asked in the last unit, is how do we tell whether we did well in our prediction problem? And everything on this slide you've seen before. You use R-squared coefficient of determination. And the motivation, again, is RSS is a nice metric, but it has a couple weaknesses. One thing is that it grows as you have more training samples. And so you want to normalize by the number of training samples to take out that variability. Second, it grows with the variance on the targets. And so you also would like to divide out that. And what you get as a remainder is something that is much more interpretable. Most commonly, you look at 1 minus that normalized RSS, which is called R squared. And as we talked about last time, when R squared equals 1, you can only get that if RSS is 0, which means you have perfect prediction. That's great, but it rarely happens. R squared equals 0, there's a couple ways to think about that. One way is that if you're using this least squares framework, you should never get anything less than 0. If you do, there must be a mistake somewhere in your code. Another way to think about it is that you can always build a trivial predictor that just, as its predictions for y hat I is just the sample mean of the targets, training targets. You can always build a trivial one that gives you 0. So, and if R squared is negative, it means that you must not be using a least squares predictor. And it's certainly possible to build non-least squares predictors that are worse than trivial. Okay. But if you see this happening in the lab, then you should know something is maybe wrong with your code. Okay. So, so we saw all that before. So now let's, again, pause to reflect on what we've done. This is the expression we derived. The problem with this expression is it's really kind of hard to tell what's going on here. So we have this matrix A that involves our training features, but it also involves this column of ones. And we can see that A is used in a pretty complicated way to arrive at the least squares solution. So at least for me, I look at this and it's really hard to get an intuition about what's going on here. What about our features is important or not important in prediction? But when we think about like what we did in the last unit, we were actually able to get some nice interpretations in terms of like covariance and variance and sample means and so on that gave us some meaning behind the prediction coefficients we arrived at. And it turns out we can do the same thing here. We just need to come at the problem in a slightly less direct way. This is the most direct way. Just make this A matrix, solve that, set the gradient to 0, get the least squares problem. But we actually can, we can get at a more interpretable solution if we take a little bit more roundabout way. So that's what we're going to do next. Okay, so in order to prepare for this, we're going to come up with a slightly different notation. So it's going to go like this. We're going to think about the first coefficient, the beta 0, differently from all the rest. And that's because it's acting in a different way. Beta 1 through beta d, they're all multiplying our features, x, whereas beta 0 is not multiplying any feature, right? So it's kind of working differently. So when we write our beta vector, in this case, this is the transpose, the row version of beta, we're going to keep beta 0 separate, and then all the other coefficients, we're going to give them this strange notation, beta sub 1 colon d. This notation is motivated by the syntax of MATLAB and NumPy, where you use a colon to index from column 1 to column d. So that's where this is coming from. But basically, this is our definition. Beta 1 through d is just all the slope coefficients, a column vector of all the slope coefficients. Okay, so if I do things this way, then when I want to write a prediction y hat, I would write it like beta 0 plus the inner product between this new beta 1 through d vector and x. Right? Because both of these guys here have dimension d. So that inner product is valid. So that's how we're going to eventually formulate things. Okay, any questions so far? Okay, so we need to revisit statistics. As we'll see, these are just generalization of the statistics we saw last time, but we're generalizing them beyond a single scalar feature to d scalar features. So the simplest ones are the sample means. So this boldface x with the bar on top is going to be the sample mean of our training data. So that's, just the average of all these xi's. Each of these guys are now vectors, right? So we're averaging vectors to get x bar as a vector. Previously, we did this with scalars. So what if I peeked inside this x bar and you looked at the first term in the x bar vector? What could can you see what that's going to be?
X1 of n.
Yeah, so if I look at the first term in here, that first term is going to be the first feature out of my d features, right? So what happens when I do this sample mean to that first term? Just get the sample mean of the first feature. That's all. So we can call that x1 bar. Okay, so that's the scalar sample mean that we saw last time. And then, the same thing happens with the second. All the way down to the last, we're going to get x bar n. So notice that there are no underlines on these quantities. These are scalars. This is a vector. Okay, so then this we saw this in the last unit. This is just y bar is just the scalar sample mean of our scalar targets. That's good. What about this? If I want to look at the deviation of my training x from the sample mean, it's no longer enough to look at a scalar variance quantity. I actually have to look at a matrix valued quantity, which is this thing called the sample autocovariance matrix. It has the same form as we saw. So down here, this is what we saw in the last unit. This was our autocovariance scalar. And that was in the case where we had a single feature xi, right? Now I'm doing this with a vector xi and a vector sample mean, but you can see it has the same form. The key thing here is I need a transpose. This is going to be a vector, a column vector. This over here is going to be a row vector, and when I multiply a column vector times a row vector, it expands to a whole matrix. Okay, so this is going to be an entire matrix, so I'm giving this a capital boldface. This is the sample autocovariance matrix. What do you think? What if you looked at the first row, first column? What would that be in terms of things we've seen before?
Variance?
The variance of x1, exactly. If I looked at the second diagonal element, that would be the variance of x2, and so on. So the diagonal elements of this guy are the variances we saw in last unit. When you look at the off diagonals, you're looking at the covariances between the different features x. But not the covariance between the features and the target. That is handled by this. So this is the sample cross covariance vector looking at how correlated our features and target are. Again, this is going to be, so this is a vector quantity, this is a scalar quantity, so in total we have a scalar quantity here. So we have a lowercase boldface s. And just for comparison, this is the one from the last unit. The only difference is that in the last unit, we had scalars down here. Okay, so with these sample statistics, we can relate beta directly to these in an interpretable way. So that's what we'll do next. Okay, any questions? Yes?
Could you repeat what the diagonals of the big S matrix are?
Yeah, so diagonal terms are, we could write them this way, like S, X, J, X, J. So this is the variance, let me say the jth diagonal term is S xj xj. So it's the variance of xj.
So what would be the use of the off-diagonal?
The off-diagonal ones? It's very important because when you have different features predicting a problem, some of them could be redundant. Some of them could be redundant in a way that they fight against each other. And if you don't sort of like get their phases aligned, that's essentially what we need to do. We need to make sure they're all working together to predict. And we have to know how they relate to each other to remove redundancies and align them together. Yeah.
I just
Question?
wanted to make sure I understood SXX and SXY correctly.
Yeah.
So the sample autocovariance matrix is the correlation among features, right?
Well, it describes, that's right, it describes the correlation among the features. The diagonal terms are the correlation of a feature with itself, which is the variance.
Right.
And then the off-diagonal terms are correlation with a feature and other features.
Right.
And then
SXY is just the correlation of the feature to the label.
to the target, to the label, exactly. Good, all right. Is everybody okay with these statistics? Okay, so the rest is a derivation that's not unlike the one we did before. I filled in a few more of the blanks, but it's not too bad, just a few pages long, so bear with me. So the first thing we need to do is we would like to come up with some alternate expressions for our autocovariance, similar to what we did last time, that are going to help us, because this particular expression is not something that's going to show up directly in a derivation, but this guy is likely to. Okay, so let's start with this. We're going to expand this quadratic, so we're going to have the first times first. We're going to have cross terms, so it's going to be like this times the sum of this is going to be this thing, or this times this, that will be this other cross term. And then finally, we have x bar times x bar transpose. This is what we call an outer product. Okay, so to simplify this, what is this term here? We have another name for this. X bar. Same with this. And now you can see this is going to be x bar transpose. This is another x bar transpose. So we have three of them, but this is a minus, and this is a plus. So these guys cancel, leaving this. So we're going to get the first term, which is the average of xi transpose minus x bar transpose. Okay, so and of course, if you want, you could move this to the other side, and you could say that whenever you have this average of this xi transpose, that's the sample covariance plus the outer product of the sample mean in itself. Okay, so we can do something similar for a cross covariance. We expand this into the 4 different terms. We notice, for example, that this guy is, what is this one? Y bar. This is another, what is this one? X bar. And now you can see that again, the 3 last terms are similar. These cancel. And we have 1 over n times the average of xi yi minus x bar y bar. Okay, so these will be useful in our derivation because we're likely to see terms like these. They often come up. Okay, is everybody okay with these expressions? Okay, so then we're ready to do the derivation. So, as usual, our objective is going to be to set the partial derivatives of RSS to 0. But now we're going to handle the partial derivative with respect to beta 0 differently from the others because it is acting in a different way. So if you remember, we're writing y hat I like this. This is actually minus y hat I. And so what happens then? If I want to take the partial derivative with respect to beta of this, first step, slide it through the sum, right? Then apply chain rule. So I'm going to have 2 times this whole thing times the partial derivative of this with respect to beta naught, which is minus 1. Okay, so we're going to get minus 2 times the sum, I equals 1 to n, of the quantity yi minus beta 0 minus x under bar I transpose times beta under bar 1 through d. Okay, so that's a partial derivative with respect to beta 0. Something similar happens with respect to beta j, but it's a little bit more complicated because when we do the chain rule, the tricky part is taking the partial derivative of this interior thing with respect to the jth beta. Right? So to do that, we actually need to kind of unpack this to expose the jth beta. So to do that, let's write this as a summation. I'm going to use something, index variable different than j, because it would be confusing if I use j, so I'll use j prime again. So I can write this as a summation over j prime of these terms are x sub I j prime, and these terms are beta j prime, where j prime is going to go from 1 through d. So now, when I take the partial derivative of this interior stuff with respect to beta j, can you see what we're going to get? What happens to this stuff? It goes away, right? It's not a function of beta j. So I can focus on this. So what is a partial derivative of this with respect to beta j? Xij. Because you have all these terms, but only one of them actually involves the same j you're using here. So and that particular one is xij times beta j. So when we finally take the partial derivative, all we get is xij. Okay, so to write the answer, we have minus 2. I goes from 1 through n of, here's the result we just derived, xij, times the same parenthesis term from above, yi minus beta 0 minus x under bar I transpose times beta under bar 1 through d. Okay, so now we have these sort of, we have these expressions, we need to simplify them a little bit. So like we did last time, we're going to get rid of the minus 2 by multiplying both sides of this equation by minus 1 over 2n. So that's going to change this minus 2 into 1 over n, and that's going to give us this expression here. Next, we can do some simplifications. We can see that this average of yi, we can call that y bar. Then we have an average of minus beta 0, that's just minus beta 0. And finally, we have an average of this. The averaging is over the I index, which will turn this xi into an x bar. And so we have a pretty simple expression. 0 equals y bar minus beta 0 times x bar transpose beta 1 through d. We rearrange it a little bit, and we find the beta 0 term must equal y bar minus x bar transpose beta 1 through d. So this is a direct analogy of what we saw in the last unit. The only difference is that x bar is now a vector, and beta 1 through d, which used to be scalar beta 1, is now itself a vector. But otherwise, it matches perfectly. Okay, everybody good with that? Okay. All right, so let's see, I think, is this maybe, yeah, this is the last page, we're almost done. So next we're gonna work on equation 2. We're gonna work on this equation here. You can use the same approach. We divide both sides, or multiply both sides by minus 1 over 2n. That's not going to change the left, but at the right, it's going to change this into a 1 over n. And that is going to give us this expression. We expand this out. We're going to get this first average of xij yi. Then we get an average of xij beta 0. But the averaging is really just on this term, so that's going to be x bar j. So to make sense of that, remember all throughout the course, I'm going to be consistent. I is going to index our samples, and j is going to index our features. So here we're fixing j, fixing feature j, but averaging over training samples. So that's going to give us x bar j, which is the sample average of our training data for feature j. Okay. And then finally, we're going to get this last expression, which is a bit more complicated. Okay, so is everybody okay so far, or any questions? Okay, so the next thing is let's replace this with the expression we derived on the previous page, which is this guy. So that's going to give us this y bar, and it's going to give us this term here. So now this might look kind of a little bit complicated, a little bit messy, but we're going to be clever, and we're going to write. So this is all these terms are scalar terms. Let's write them as the jth entry of a vector. So for example, this is an easy one. This is the jth entry of this vector, right? This y bar is just a scalar, so I really just need to say this is the jth entry of this vector. Similarly, this is the jth entry of this vector. This is a vector of all the different features for sample I. And same thing happens here. This is the jth entry of this column vector. So that allows us to rewrite these things in terms of more familiar quantities, which we've seen before. And finally, we can actually use some of the expressions we derived. Does anybody see, for example, this thing? Does that look familiar?
SXY.
Yeah, that's our SXY. So let's see, where am I? So we have, this again is going to be the jth entry of the vector SXY. And what about this other part here? Okay, so we got a couple things, but we have beta I 1 through d on the right side, so I can really move this into this parenthesis, right? At which point I get this minus this. Does that sound familiar?
SXX.
Yeah, capital SXX times beta 1 through d. And again, this is a scalar 0 here, which is the jth entry of this matrix. But the key thing is this must actually hold for all the j, not just this particular j, which means that this entire vector should be 0. Another way, if that entire vector is 0, what does that tell me about beta 1 through d? Does anybody see how to get beta 1 through d? I guess we could rewrite this. This is equivalent to SXX beta 1 through d equals SXY. Right? I just moved, all I did here is I moved this to the left side. So if we're given this and I want to solve for beta 1 through d, what do I do? Yeah. Multiply on the left by SXX inverse, assuming it exists. That isolates the beta, and on the right we get SXX inverse, little s x sub y. So this is assuming that this covariance matrix is invertible. Not always the case, especially if you don't have enough data for the number of features you have. In any case, we will assume for now that we do. And we're essentially all done. We just need to put our results together. We have this expression for beta 1 through d, and then we have a previous expression for beta 0. So altogether, we can write the least squares solution, beta ls, as this vector whose first element is beta 0 and whose remaining elements are beta 1 through d. And now I'm just going to plug in the expressions like this. So this is a scalar on the top, and this is a column vector on the bottom. Okay, so it might look a little bit complicated, but actually, if we compare it to the expressions from last time, which we can write like this, so beta 0 in the last unit, this was y bar minus x bar sxy, which in that case is a scalar, divided by sxx. And beta 1 was sxy divided by sxx. So these are scalar divisions, right? But hopefully you can see how this directly corresponds to this. So with matrices, I can't write sxy, sxx when this is a matrix. We never do that. So instead, I have to invert the matrix and multiply the front of this. Essentially, I need that all the dimensions match. So I'm going to have a row vector, a matrix, and a column vector. That's what we have there. Or down here, I have a matrix times a column vector. So, but you can see that in the case that this was a scalar, you could rewrite it like this. Okay, so everything agrees with what we did before. It's just we have a more general case which involves more than one feature. All right. Okay, so that was the hard part. So what we'll do in the next unit is we'll get into how to do all this in Python, and we'll revisit our demo for this unit, and we'll see how this works on our diabetes data. But that's it for today. See you guys on Friday.